In this video, we look at the variational principle, which is at the heart of many computational methods that calculate wave functions for atoms and molecules. Look at the Schrödinger equation for the ground state of an atom or molecule. H hat operating on uppercase psi 0 equals E0 times psi 0. Here, E0 is the ground state energy and psi 0 is the ground state wave function. We can recast this into an equation for calculating the energy. Let's pre-multiply both sides with psi 0 star and then integrate over the entire range of all coordinates. After rearranging, we get E0 equals to the integral over psi 0 star h hat psi 0 d tau divided by the integral of psi 0 star psi 0 d tau. The integral symbolizes integration over the full range of all coordinates. For a system with n electrons, this would be 4 times n coordinates, 3 spatial and 1 spin per electron. We are also keeping the integral in the denominator. For a normalized wave function, this would be of course equal to 1. But for the approximation method we are going to use, it is convenient to disregard the normalization during the calculation and only normalize the wave function at the very end. In bracket notation, this is bracket psi 0 h hat psi 0 divided by bracket psi 0 psi 0. The main problem with this equation is that we need the wave function in order to compute energy. But for atoms and molecules except for the hydrogen atom, we don't know the wave function. Now, there's a beautiful and fortunate theorem that helps us out. It says the following: replace psi 0 in this equation with any other function psi tilde that approximates the wave function. And calculate the corresponding energy. E tilde equals to bracket psi tilde h hat psi tilde divided by bracket psi tilde psi tilde. The theorem states that this energy, E tilde, is always greater or equal to the exact ground state energy. The equality sign, E tilde equals E0, holds only if the approximate wave function is actually equal to the true ground state wave function. This is the variational theorem. It is very useful. It says that no matter what wave function we choose, no matter how bad our choice is, we will never calculate an energy that is smaller or lower than the true ground state energy. In some sense, an approximate wave function that gives a lower energy is better than an approximate wave function that has a higher energy. This gives us a simple recipe for calculating the ground state wave function for atoms and molecules. All we need to do is to set up a wave function that depends on some adjustable parameters, and then vary the parameters until the energy E tilde is minimal. For example, let's construct a trial wave function. Psi tilde that depends on parameters C1, C2, and so on. These parameters are called variational parameters. For this wave function, the energy will depend on the variational parameters, and the variational principle will read E tilde of C1, C2, and so on, larger or equal to E0. If we optimize each parameter so as to minimize the energy E tilde on the left, we will get as close as we can to the exact ground state energy E0, and we'll have an approximate solution for the Schrödinger equation. So, we take an adjustable wave function and minimize its energy E tilde with respect to the variational parameters C1, C2, and so on, to obtain an approximate ground state wave function psi 0 and an approximate ground state energy E0. This method is called the variational method. Now, how to approach this minimization? One way is to set the derivative of E tilde with respect to each variational parameter C equal to 0. Here is a brief example. Let's look at the hydrogen atom. Assume for now that we don't know the exact form of the ground state wave function. Let's make an educated guess and try a Gaussian function. Psi tilde equals to e to the negative c1 r squared. Here, c1 is the only variational parameter. We can calculate e tilde and then determine its minimum with respect to c1 by setting the derivative delta e tilde delta c1 equal to 0. The solution is c1 equals to me squared e to the fourth divided by 18 pi cubed times epsilon 0 squared times h bar to the fourth. The final normalized approximate wave function is psi tilde equals to 2c1 over pi to the power of 3/4 times e to the negative c1 times r squared. The approximate energy, E tilde of C1, equals to negative 11.6 electron volts, which is larger than the exact ground state energy E0, which is negative 13.6 electron volts. However, the approximation is pretty good given the roughness of our initial guess. In summary, 3 things are important. First, the variational theorem says that any approximate ground state wave function, no matter how bad, has an energy that is larger or at most equal to that of the exact ground state wave function. Second, the variational method utilizes this theorem to calculate approximate wave functions and energies for the electronic ground state of atoms and molecules. Third, the method uses a wave function that can be varied and determines the minimum of the energy with respect to the variational parameters.